Alright, so in this video we go over section 6.2 trigonometric functions, how to find these values using the unit circle approach. So what we do in this section is to define what a unit circle is, what their elements or parts are exactly, and find the values of the most common or most important angles, which is in this case the quadrantal angles, 45, 60, and 30 degrees, and of course as well as their multiples, and then putting everything together. Alright, so first of all, the unit circle, it's a circle of radius 1, that's why the name unit, and whose center is the origin of the coordinate system, and all the points that go around the circle are related to the angle T that is formed from the positive x-axis and that point. Okay, so here's a picture to relate that. So here is the x-axis, and then when we look for a point, well, that's going to form this ray right here, forming an angle that for the moment we're going to call T. So we're going to find essentially six trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. But let's start with the two basic trigonometric functions, which are sine and cosine. The other four actually come from these two. So in this case, well, this point that goes around the circle has two components, an x component and a y component. And in this case, the sine function, which is denoted sine t, is going to associate the angle t with the vertical component, or the vertical coordinate, that is the y coordinate of the point, and the angle, as opposed to the cosine function denoted cos, t associates the horizontal coordinate of this circle. So in this case, that means that this collection of points will have, so we are going to relate x with cosine and y with sine. So that when we read the unit circle and its values, that's how we're going to read it. Alright, so let's go over the definition of the remaining trigonometric functions. Well, so we have the point x, y that we defined in the previous page, in which x is the cosine and y is the sine. I'm just going to use c and s for short, and it corresponds to the angle t. So the tangent function is the ratio y over x, which in this case is sine over cos. Again, keep in mind, sine is y, cosine is x, y over x, sine over cos. Cosecant is actually the reciprocal of sine, which in this case, well, we can further define it as, well, x over y, because that's the reciprocal of tangent. And the secant function, it's actually, the secant function is the reciprocal of cosine. Well, cosine is x, secant is 1 over x, which is 1 over cos. And last but not least, oh wait a minute, that's not the one, that's cosecant. That's the cotangent function, that's the one that is x over y. Never mind, it was already there. So suppose we have a point in a unit circle whose x equals cosine is that negative 1/5 value, and the y value that sine theta. To be a point on the circle that has well, t. We're not really interested in the angle. We are in the actual per se. We're looking only for the values of the trigonometric functions of the angle. So let's find the values of the following. In this case, sine, which is given right here. That's simply, well, it's actually t, not theta. I should have said t. So sine theta is only the y component, to square root of 6 over 5. And cosine theta is simply the x component. So we don't really have to do any calculations, just state the values. Now, tangent, which is defined at, we define it at the top, that's y over x. All right, so that's, it would be worth to say y over x. So y, which is 2 root of 6 over 5, the whole thing divided by negative 1/5. And the nice thing about this calculation right here, when we perform that calculation, it is these 5's are going to get canceled, and we simply have 2 root of 6 over 1, which is simply 2 root of 6. But don't forget this negative value right there. All right. So let's see what's next for this. It's a little bit too dark for the bottom. Let me get more lighting here, hopefully. Okay, so that didn't help much. All right. So cosecant t. Cosecant, it's the cosecant function is basically the reciprocal of sine, or 1 over y. So I'm just going to write 1 over y. And then, well, 1 over the y component, which is 2 root of 6 over 5. That's a 1 over 2 root of 6 over 5. But we need to find the reciprocal of this. We cannot just leave it like this. So that's going to be 5 over 2 root of 6. Okay, so this might be an okay answer. I mean, a good final answer. However, in this case, you might want to rationalize the denominator, because when you put this on MyMathLab, when you do your homework, this may not be taken as an okay answer. It's going to say, although the answer is correct, it's not in the correct format, because most likely you need to rationalize the denominator. And we do that by multiplying numerator and denominator by the same radical. So when we multiply this together, the radical goes away. So what's going to happen here? Well, so this is going to be 5 times the root of 6, which is 5 root of 6. And then square root of 6 times the square root of 6. Well, square root of 6 times square root of 6 is square root of 6 squared. But when we square a square root, this cancels. That becomes a 6. So that's going to be 2 times 6, which in the end, that's going to be 2 times 6, which equals 12. Final answer for this guy. Let's define secant. So just like cosecant is the reciprocal of sine, secant is the reciprocal of cosine, 1 over x. Let's go up here. Secant is 1 over x, the reciprocal of cosine. So, and again, cosine is related to the x coordinate, which is negative 1/5. That's 1 over negative 1/5. And well, dividing by a fraction, well, it's the same as multiplying by the reciprocal. This is simply negative 5. There's not much to do here. Cotangent, on the other hand, that's this first example. That's x over y, which is the reciprocal of tangent. So if tangent was y over x, well, then the reciprocal has to be x over y. And in this case, negative 1/5 over 2 root of 6 over 5. And that's going to get us canceled these 5's, leaving us essentially with negative 1 over 2 root of 6. But we need to rationalize this denominator, actually. It would be a good idea if we do. Okay, let me fix the lighting issues here. Much better. So, I need to multiply this by root of 6. Root of 6. Okay, so root of 6 times itself, it's going to be 6. Negative 1 times root of 6, and 2 times 6. Don't forget the negative, which is 12. So negative root of 6 over 12. So that gives us the 6 values for the trigonometric functions in this case. All right, so let's go over another example here. So let's move on. Let's turn the page. So, well, let's redefine the trigonometric functions as functions of angles. Well, and initially we defined the functions for an angle t, but in this case we consider that t as any real number. All right. However, in this case, all we're going to do here is just change the notation from t to theta because we're going to talk about angles. So angles, the symbol that we use most of the time for angles, right, is the symbol theta, as opposed to, you know, any other parameter or any other number, any other real number. We use the symbol t, but ultimately they are all real numbers. But just again, just to denote them as angles, we use the corresponding symbol, the most typical one to use. All right, so trigonometric functions of quadrantal angles. First of all, what's a quadrantal angle? Quadrantal angles are angles that lie in between two quadrants. Like, for example, the angle that lies in between quadrant 1 and 2 is the 90-degree angle. The number that lies between quadrant 2 and 3 is the 180-degree angle. All right. Another quadrantal angle, the one that lies between quadrant 3 and 4, is the 270-degree angle, and either 0 degrees or 360 degrees, depending on how many times you go around. Okay, so that's the angle that lies between the fourth quadrant and the first quadrant. All right, it's not an angle that lies in any of the spaces here, in any of the quadrants. It's actually the one that lies in the middle. Okay, so let's find the exact values of the 6 trigonometric functions of theta equals, notice I'm writing 0 in radians, which is the same as 0 in degrees. All right, so let's list. Sine theta, sine of 0 actually, cosine of 0, tangent of 0, and cotangent of 0, secant of 0, and cosecant of 0. All right, so let's find out the corresponding, well, in this case we need to know what the x value is for 0 degrees and what the y value is, and it's given here. Well, we're given for 0 degrees, 0 degrees, we have basically the positive x-axis, in which x equals to 1 and y equals to 0. And keep in mind again that the x component is cosine and the y component is sine. All right, so the first two are really easy to answer. Cosine of 0 is 1 and sine of 0 is 0. And then we need to define tangent again from the previous page. Tangent is defined as y over x. In this case, well, y over x, which is 0 over 1, that's a 0. Cotangent, which is the reciprocal of tangent, and it's x over y as opposed to y over x, which is tangent. So x over y, in this case, well, x, which is equals to 1, and y, which is equal to 0, that's 1 over 0. Well, can we divide by 0? So no, undefined. All right. Now let's do secant. So secant, according to our formula, secant is defined as 1 over x, or the reciprocal of cosine, 1 over x, which is 1 over 1, which is 1. All right. And finally, last but not least, cosecant, which is 1 over y. Okay, where do we get that from? From here, 1 over y. That's the reciprocal of sine. So that's a 1 over 0. And in this case, well, we cannot divide by 0 again. So this will be undefined. Let's repeat this exercise for the exact values of the 6 trigonometric functions of pi over 2, which is 90 degrees. So now we have the picture for 90 degrees, and the point that corresponds is x equals to 0 this time, and y equals to 1. Okay, so let's define sine of pi over 2, cosine pi over 2, or 90 degrees. Either way you represent it is fine. And tangent pi over 2, cotangent pi over 2, secant pi over 2, cosecant pi over 2. And well, let's find out what those actual values are. Alright, so in this case, well, x, as usual, x represents, is linked to cosine, and y is linked to sine. So the first two are actually answered from this value. So sine equals to 1 and cosine equals to 0. Okay. Now tangent, which is y over x. In this case, well, y over x, that's y 1 over 0, and in this case it happens to be undefined. Okay, undef, that's fine. Cotangent, on the other hand, it's the reciprocal of tangent. Instead of y over x, that's an x over y, and in this case we can divide 0 over 1. That's going to give us a 0. Secant pi over 2, that's the reciprocal of cosine. Well, if cosine is x, well, then this is 1 over x. Or again, keep in mind the formulas secant 1 over x, which is 1 over cos. And then, well, in this case, 1 over the x coordinate, which is 0. Well, that's another undefined. Last but not least, for this example, well, that's going to be cosecant pi over 2. Well, that's 1 over y, which is 1 over the reciprocal of sine. Well, it's right here, cosecant 1 over y. And in this case, well, that's 1 over the sine value, 1 over 1, which is 1. All right, so examples 4 and 5. Well, there's a couple of very silly typos here. This one was supposed to be pi or 180 degrees, but I'm gonna skip this one. Well, this one was supposed to be over here, not there. I'm gonna skip this one. That's the point -1 comma 0. You can repeat this exercise on your own, and then the next the exercise on the next page, which is actually not pi over 2. That's 3 pi over 2, and in this case this is 270 degrees, and instead of going in this direction it goes down here to the point 0 comma -1. Of course, I mean, if you want to fill in the blank, sine, cosine, tangent, cotangent, secant, and cosecant, and get them from the graph, that's fine. However, they are all summarized in here. You're not required to really memorize all of them, but I mean, in practice, as we use them, because we're going to use them a lot, quite a lot. Well, in a way, you will have this memorized, right? But you don't have to sit down right now and memorize and recite them, each and one of them. With this, like I said, this will come in practice. Now let's find values of other angles. Let's find the sine of 3 pi. Well, what's 3 pi first of all? I have the picture right here, right next to us on this. We start at the positive x-axis, which is 0, and then we're going to do one turn. That one turn will symbolize 2 pi, and then we keep going to another half rotation, which is actually pi. Well, combining all this is 3 pi, but in this case this is the same as saying pi, the one that has p equals -1 or -1 comma 0. Keep in mind that this is cosine for x, and sine is our what is the y value. So answering the question right here, sine of 3 pi is the y value, which is simply 0. There's really not much to do. We go with the picture. Okay, let's be very careful with the next one, because keep in mind, as we looked in the previous section, we can go in the negative direction as far as angles go. So it's 270 degrees. would be in this direction all the way here. However, in this case, we're going in the negative direction. We're going negative 90, negative 180, and negative 270, which is precisely the same as positive 90 degrees. And again, the same. This is cosine, and this is y, which is actually sine. All right. What are they asking us for? Well, to find the cosine of negative 270 degrees. Well, what do we have? 0 as well. All right. Okay, so that covers finding the trigonometric functions of quadrantal angles, which is again 0, 90, 180, and 270 degrees. Okay, let's look for other very, very popular angles that we are going to use. 45 degrees, which in radians is pi over 4. So we're going to consider the picture below. Well, so what about that picture? So in this case, if we look for 45-degree angle, it's actually, this point will actually intersect with the line y equals to x. All right. So keep in mind that this is a unit circle right here. What we're going to do to find the values of x and y is basically to find the intersection points between the unit circle and the diagonal line y equals to x. So in other words, find the intersection points or solve this given system. Y equals to x, and x squared plus y squared equals to 1. That's a nonlinear system. Well, we're going to get a little bit more in depth with this kind of systems later in the course, although you may have done already some of them back in your intermediate algebra course. But in this case, it's going to be really, really simple to do. So what I'm going to do is essentially replace this y equals x in here to make it x squared, plus instead of y squared, that's also x squared equals to 1. Combine like terms, that's 2x squared equals to 1, x squared equals to 1/2, and then x equals, if we take the square root on both sides, don't forget plus minus on the right hand side, that's the square root property, that's plus minus the square root of 1 over square root of 2. And in this case, well, you might want to take only the positive component because we are in the positive x-axis. Of course, the negative will come into play when we move to other quadrants. So for now, let's just consider the what's this called? The positive solution. So rationalize the denominator to get in the first place 1 times the root of 2. That's root of 2, and root of 2 times itself, the radical cancels essentially, and x equals the square root of 2. So square root of 2 over 2, that's x. Now we need to find y. Well, so y equals to x, y equals to whatever x is, that's also square root of 2 over 2. No need to back substitute in this complicated equation. Of course, you're going to get the same, but why do the hard way if we have simply that y equals to x? So this is also square root of 2 over 2. All right. So let's find the exact values of the 6 trigonometric functions of 45 degrees. Well, so again, let me write them down in a different color using actually a unit circle here. Okay, so this is the point square root of 2 over 2, comma, square root of 2 over 2. Okay, that's for 45 degrees. Okay, so let's list every single one of them. Sine pi over 4, cosine pi over 4, and tangent pi over 4. Then we are going to define cotangent of pi over 4, secant pi over 4, and cosecant pi over 4. All right, so let's go with this circle right here. So keep in mind again that the x component is our cosine and the y component is our sine. It's our sine function. All right, so sine is simply root of 2 over 2. Got it. Cosine root of 2 over 2 as well. Got it. All right. Tangent pi over 4. Tangent pi over 4 is y over x again. And in this case, root of 2 over 2 over root of 2 over 2. Well, essentially dividing the same number, dividing a number by itself, they cancel to give us a 1. Cotangent, which is x over y, on the other hand, well, what do we have? X over y, which is the same, square root of 2 over 2 over square root of 2 over 2, and that's also 1 because same number, divide by itself, that's 1. Secant pi over 4, that's 1 over x, that's the reciprocal of cosine. So if cosine is root of 2 over 2, its reciprocal is going to be this, but this is ugly looking, and we need to fix this guy. So that's going to be 1 over a fraction is the same as the flipped fraction, which is 2 over root of 2. But again, you don't want radicals in the denominator. Root of 2, rationalize the denominator. 2 root of 2, that's simply 2 root of 2. But root of 2 times itself, that's 2. The nice thing, these go away. Root of 2. Final answer. Last but not least, cosecant of pi over 4, that's the same as 1 over y, which is 1 over, square root of 2 over 2. Okay, I don't want to do the same process again because it's exactly this one, so this is also square root of 2. All right, it's the same. Why do it twice? All right, let's find the exact value of the expressions below here without actually using a calculator in this case. So we're going to use the identities that we know so far. All right, and then we are going to, and the not identities but the values. Okay. So sine 45, well, we did it at the top here. Sine of pi over 4, that's square root of 2 over 2. And cosine of 180, so for cosine 180, we got from the previous page, well, you can use the table, 180 degrees, cosine is negative 1. All right, that times negative 1, giving us a negative root of 2 over 2. Secant of pi over 4 plus cosecant of pi over 2. Well, what is secant pi over 4? We already did it here. Secant pi over 4 is simply root of 2 plus cosecant of pi over 2. Well, we did that in a couple of pages ago. I think we did it here. Cosecant of pi over 2, that's 1. All right. And well, square root of 2 plus 1 is simply square root of 2 plus 1. There's nothing really to simplify about this one. All right. Oh, hold on a second. Actually, yes, this one has to be squared. And boom, boom, they cancel. That's 2 plus 1, which adds up to 3. Final answer is 3. And the last example, sine of pi over 2. Well, this sine of pi over 2, that's the square root of 2 over 2. I'm going to put parentheses, another parentheses. Cosine of pi. Well, we already did cosine of pi or get it from the table. For pi, cosine is negative 1. All right, again, pi, which is 180 degrees. Go to the cosine column, that's negative 1. In fact, we did it at the top, but at the top we did it in degrees. Here we do it in radians. Minus the sine of 3 pi over 2. What's 3 pi over 2? Well, 3 pi over sine of 3 pi over 2. 3 pi over 2, sine is negative 1. So let's go ahead and do that one. So minus negative 1. Be careful here. So you might want to use the smile rule here. Alright, and positive times a negative is negative root of 2 over 2 plus 1. And well, we cannot essentially combine this unless you want to combine this by multiplying by the LCD. And that's going to give us simply 2 minus root of 2 over 2. Final answer for these guys. All right, let's move on to the next section. Well, so finding the exact values of the trigonometric functions of pi over 3, which is 60 degrees, and pi over 6, which is 30 degrees. Well, let's consider a right triangle. All right, let's consider a right triangle, an acute right triangle, in which the largest of the acute angles is 60 degrees. The smallest of them is 30 degrees, and of course, because this is a right triangle, this is 90 degrees. So what we're going to do here in this case, well, we are going to find the values of A and B, the values for 30 degrees, and which actually you can see them below. Well, I mean, not that I mean to spoil the final answer, or in fact you may have seen this before, you know this, but well, where do we get this from? Well, so if we extend this to an actual equilateral triangle in which the side C is 1, 1, 1, but in this case this side A gets duplicated. See what I'm saying? When we duplicate this triangle, this A is essentially duplicated. It's a duplicate of itself. So from here we can say that C, which equals to 1, is equals to 2A. All right, C equals to 2A, and in this case we know that C, since C equals to 1, well, 2A equals to 1, which means that A equals to 1/2. Okay, so let me put this right here. That's 1/2. I'm going to figure out the B side. And how are we going to do that? Well, we know from the Pythagorean theorem that A squared plus B squared equals C squared. We need to find out the B side. We know A equals to 1/2. Let's square that guy. And C equals to 1. 1 squared is simply 1. 1/2 squared, that's 1/4. Solving for B, we get B squared equals to 1 minus 1/4. And this is the same as saying 4/4 minus 1/4, that's 3/4. And then when we apply the root property, the square root property, B equals to the square root of 3/4. Notice I'm skipping the plus minus in this case because we're looking at a geometric figure, in this case a triangle, and in this case, well, the length of the sides of a triangle are supposed to be positive. But if we were just solving a plain vanilla equation, well, in that case we need to be more strict with the plus minus. All right, well, we need to apply the square root, the properties of the quotient rule for radicals. Square root of 3 over square root of 4. Square root of 3 is simply square root of 3 because it's not a perfect square, as opposed to square root of 4, which is 2. So square root of 3 over 2, that's going to be our B value. All right, so that's where this is coming from, the square root of 3 over 2, and this 1/2 for the 60 and this 30-60 degree triangle. All right, so now let's put everything together. So if these were, okay, let me just give you a rough picture. If these were the actual circle, okay, let me extend this to the circle. What, it would go all the way here, it would go all the way there, right? I'm interested in this point in which x is 1/2 and y equals square root of 3 over over 2, which is no other than the picture in the next example. So let's find the exact values of the 6 trigonometric functions of pi over 6, or 60 degrees. So sine pi over 3. What's sine? Keep in mind, as usual, this is x equals cosine. This is y equals sine. That's always the same case. So sine is the y coordinate, which is square root of 3 over 2. Cosine, which is the x coordinate, that's 1/2. We're done. Tangent, which is y over x as usual. Again, that comes from the formula that we discussed earlier in this section. But what's the y value? That's square root of 3 over 2 over the x value, which is 1/2. Again, something nice is going to happen here. The 2's are going to go away. And square root of 3 over 1, that's simply square root of 3. Final answer. Okay, we're done with sine, cosine, and tangent. Let's do cotangent. Cotangent of pi over 3. Cotangent of pi over 3, which in this case is going to be the reciprocal of tangent x over y. And in this case, well, let me put everything together. So x, which is 1/2, over the y value, which is square root of 3 over 2. What's going to happen here? Well, cancel these 2's. 1 over square root of 3, which is, again, oh, in this case, be careful. We need to rationalize the denominator. You don't want those radicals in the denominator for 3, at least not in this section. And, well, that's going to be square root of 3 over 3. Okay, final answer for this. What else do we need to do? Well, we need to also do secant. Secant pi over 3. Secant is no other than 1 over x, which is 1 over cosine, in other words. 1 over 1/2. Dividing by a fraction is the same as multiplying by the reciprocal, that's simply 2. And last but not least, we need cosecant of pi over 3. Cosecant pi over 3, which is going to be 1 over the y coordinate, which is 1 over square root of 3 over 2. But again, this is 2 over the square root of 3. But we need to rationalize the denominator in this case. All right. Let's see. So that's 2 root of 3. And square root of 3 times itself is simply 3. Final answer over here. All right, so this is where all the 6 trigonometric functions come from for the pi over 3 or 60-degree angle. All right. Okay, so in this case, this is basically a repetition. Oh, I don't know why I did repeat. This was supposed to be pi over 6, which in this case is 30-degree angle. All right, so pi over 6. And in this case, well, let's see. Let me see if I have the summary. Well, it's the way we would get sine, cosine, tangent, cotangent, secant, and cosecant for the 30-degree angle is exactly the same. I'm gonna leave it blank if you want to do it on your own. But ultimately, all these values are right here in the next table. I mean, I don't want to make this video too long. All right, so let's verify. For pi, we already did for pi over 3. Pi over 3, what's sine? Sine is square root of 3 over 2. Let me put this together. Square root of 3 over 2, that's sine. Cosine is 1/2. Cosine is 1/2. Tangent, which is y over x, we already simplified all this to square root of 3, which is right here. It checks with the table. Cosecant is square root of 3 over 3. Where is it? No, cotangent is square root of 3 over 2 over 3. Secant is 1 over x, which is 1 over a half, which is 2. That's secant. And cosecant, that's 2 root of 3 over 3, 2 root of 3 over 3. Okay. In the same way, you can get the values for pi over 6. Some of them are just going to be changing places because of the reciprocity, the property of being just reverse in a way. And for the 45-degree angle, we already did that, so these tables pretty much summarize everything. All right, so what have we been doing in this example? So we have been finding the values of the trigonometric functions for 60 degrees, 45 degrees, but only in the first quadrant. In the first quadrant, all of the values are positive. However, we are going to be in the need of finding the values of the trigonometric for multiple integers of, in this case, of pi over 6, which in this case is 30-degree angle, pi over 6, 60-degree angle, or pi over 3, and 45-degree angle, which is pi over 4. All right. So if we go around the circle, when we do 5 pi over 6, well, that's a multiple of 30. If you look at the values, the x value and the y value, they are all the same, but depending on their position in the coordinate system, well, in this case, if you look at this value at this point right here, is x is negative, y is positive. A point in the third quadrant, they are both negatives. A point in the fourth quadrant, x is positive, y is negative. And it's the same for the 60-degree angle and the 45-degree angle. Look at the signs: negative, positive, negative, negative, positive, 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 negative. All right. Now, so this is this picture right here gives us an overview of each separately for 30, 60, and 45 degrees. If we imagine we can sandwich these three pictures and put them on top of each other, we would get the unit circle. We get everything together. All we need to use, this is going to be our reference for the rest of the following at least 3 chapters. So we're going to do a lot of calculations of trigonometric functions, and this is what you want to rely on. All right. So pi over 6 and a multiple of pi over 6. Do you see these are specular images? Well, what changes? They're trigonometric functions in this case. Cosine and sine, they are the same. What changes is simply their signs depending on their location on the coordinate system. So let's just, you're not required to memorize this this unit circle, although there's a lot of very useful tricks. There's a lot of videos out there explaining some sort of shortcuts, if you will, to memorize all this. However, just be sure to know how to use it. All you need to know that the x coordinate corresponds to cosine, and the y coordinate corresponds to the sine function. All right, that's all you need to know. Keep in mind that the remaining functions, okay, so this is cosine, sine, tangent is sine over cosine, cotangent is cosine over sine, and the reciprocal of cosine is secant, the reciprocal of sine is cosecant. That's all you need to know. Let's put this in practice. Cosine of pi over 4. In this case, we're going to go to 5 pi over 4. Okay, 5 pi over 4, where is it? 5 pi over 4. That's 3 pi over 4. 5 pi over 4. Okay, they're asking us for cosine. Cosine, keep in mind that that's the x-coordinate, and the y-coordinate is sine. So cosine of 5 pi over 4, that's negative root of 2 over 2. Sine of 135 degrees. In this case, we're looking for some sort of y-coordinate. as opposed to an x coordinate. So we're going to go, well, depending on the notation, sometimes we may be given the values in degrees, sometimes in radians. All right, so 135 degrees. That's the point corresponding for 135 degrees. And because we're looking for sine, you're looking for the y value, which is the square root of 2 over 2. That's all we do. No calculation needed. Just identify it from the unit circle. Although be very, very careful when it comes to negative angles. So in this case, since as opposed to going in this direction counterclockwise for negative pi over 4, you might want to go in the clockwise direction. So negative 45 degrees, that's what negative pi over 4 is. So negative 45 degrees is the same as 315 degrees or 7 pi over 4. And in this case, we're looking for the sine function. In this case, cosine, sine. Sine of 7 pi over 4 or negative pi over 4, that's the same as negative root of 2 over 2. All right? That's all we need to do. Cosine of 8 pi over 3. Well, be very, very careful with this one. So 8 pi over 3. So in this case, this is pi over 3, 2 pi over 3, 3 pi over 3, which is simply pi, 4 pi over 3, 5 pi over 3, 6 pi over 3, which reduces to 2 pi, 7 pi over 3, 8 pi over 3. So this is really 8 pi over 3 right here, right? So that's what you want to look for. Well, in this case, well, I'm gonna make sure I can erase this guy there. So let me see if I can, if it works for this guy. No, it's not gonna work. Never mind. We're looking for cosine of 8 pi over 3. In a way, we're looking for some x value related to that point, and the x value is cosine, which is negative 1/2. Final answer. Tangent of 315. Finally, some tangent here. So finally, in this case, where we're looking for y over x of whatever point related to 315. Let's look for 315. 315, which is right here, which is 7 pi over 4. This is our x, and this is our y. And y over x for this point is negative root of 2 over 2 over x, which is positive root of 2 over 2. But everything is going to cancel out. Boom, boom. Except for the minus, that's negative 1. Cosine of 210. Now in this case, we're looking for 210 degrees. Well, it's right there. What are we looking for? Well, this is cosine, this is sine, this is x, this is y. Alright, so for cosine is the x value, simply root of 3 over 2. So that's the point of this exercise, to be able to identify what the angle is, whether it's given in radians or in degrees, and find the corresponding trigonometric values, keeping in mind that the x component is cosine and the y component is the sine value, or the y value. Okay. So let's, how do we find them using a graphing calculator? And this might be a little bit tricky when it comes to perform this type of calculations, because number one, we need to make sure that our calculator is in the correct mode. That is our graphing calculator in radians, or is our calculator in degrees? Okay, let's highlight. This is very, very important. So we want to go to the mode. Okay, so our calculator is equipped to only calculate sine, cosine, and tangent. But of course, we know formulas to calculate cosecant, which is the reciprocal of sine, and secant, which is the reciprocal of cosine, and likewise for cotangent, which is the reciprocal of tangent. All right, so let's let's evaluate this. Let's find the values of these trigonometric expressions, and don't be fooled by this, because cosine of 50 of 15 with a circle is different from sine of 15 without the circle. And in this case, cosine of 15, when you see the circle, that means degrees, and you might want to make sure that your calculator is set to be in degrees. To do that, you're going to click the button for mode, and notice, scroll down a couple of times. Notice the radian mode is highlighted. You might want to scroll to the right, click enter to make sure that the calculator is in degree mode. Second, quit, and let's go ahead and do the calculation for this. So cosine of 15 degrees, oh, it's right here. So all we do is simply press the cosine button and type the number 15 and close the parentheses, click enter, and the cosine of that value is 0.9659, and we want 2 decimal places, so this is going to be 0.97. Let's evaluate sine of 15. However, in this case, be sure that this is this is degree. Note, this is in degree, and note that this is in radian. So what we want to set our calculator back to radian mode. So second, quit, and then evaluate sine of 15 in this case, and that's the value that we get, 0.6502 rounded to 2 decimal places. That's simply 0.65. Alright, let's evaluate tangent of pi over 12. Notice in this case we don't have any degree symbol. That means this is required to be used the radian mode. Alright, so we're still in radians. We're good to go. Simply type tangent of a second pi and divide that by 2, or 12 rather. Close parentheses. 0.2679, 0.27 when we round this to the next to 2 decimal places. Okay, what about secant? Like we described in the box above, we don't have a direct secant of 10. Number one, need to be sure that in this case, well, we don't see the degree symbol. This means that this is also in radians. This is also in radians. But before we can plug, we don't have a secant function. We need to convert this to 1 over cosine of 10. And again, it's in radians. So what we're going to do is 1 divided by, and press the cosine function and cosine of 10. That's negative 1.1917. Well, rounded into decimal places, that's negative 1.19. Negative 1.19. All right. Now this pretty much concludes finding the values of using a unit circle. But of course, can we extend this to evaluating trigonometric functions for circles with radii other than 1? Of course. And why can we do that? Well, because let me flip the page. So, for example, okay, I have the unit circle here. I'm just going to draw it as r equals to 1, whatever value is. For example, if I say 45 degrees, right? If I make this circle bigger, let's say to a radius of r equals to 3, well, all I did in this case is change the length of the radius. However, the angle remains exactly the same. So whether you work with a unit circle or a circle of radius 2 or a circle of radius of radius to 4, the trigonometric functions will remain exactly the same because we would have the same angle, 45, 45. Well, it doesn't look pretty. Let's assume this is also a 45-degree angle. And we are going to take advantage of that to evaluate functions over other kinds of circles. Notice in this case, well, we have the same function, the same formulas. Sine, which is in this case y over r, x over r. Well, in this case, in the unit circle, that r used to be 1. Now, in any other circle, well, we're going to have whatever the radius we have. And as an example, right here, let's call this, well, ultimately, we're not gonna care about the angle, so that's a sine theta, cosine theta, tangent theta, cotangent theta, secant theta, and cosecant of theta. All right, so what are we going to do? Well, in this case, we have that x equals to 4. Let me just make this bigger. Y equals to -3, and the radius of the circle, this is a radius, this is a circle of radius equals to 5. All right, so using the formulas, well, that's sine, which equals y over r, that's -3 over 5. That's all we do. No need to simplify anything further. Cosine, which is x over r. That's the x is 4 and r is 5. Boom, we're done. Tangent, tangent is y over x, which is -3 over 4. We're done with this guy. And cotangent of theta, that's the reciprocal x over y, which is -4 over 3. Secant, which is r over x, that is the reciprocal of that, guys. Or the reciprocal of actually cosine, not just that guy. It's called cosine. That's r over x. Simply invert this number, 5 over 4. And cosecant, which is the reciprocal r over y, the reciprocal of sine, which is 5 over -3, which gives us -5/3. Now, so this is actually related to the SOHCAHTOA idea when we relate the trigonometric functions to that idea of the sides of a triangle. But where's the triangle here? Well, this point right here can be projected this way in order to form a triangle. And if this is the angle right here, this is the opposite side, this is the adjacent side, and this is the hypotenuse. Adjacent, opposite, hypotenuse. If you have seen this before in terms of this is just a little extra to the section. We're not going to do that conventional ultimately, but just relating to this. Sine, which is y over x, this is the opposite, the y over the hypotenuse. X, which is the adjacent, that's adjacent over hypotenuse. And then opposite over adjacent, adjacent over opposite, and then hypotenuse over adjacent, and finally the hypotenuse over the opposite. But in this case, well, that's just pretty much to put that together into their corresponding triangle. But that's not how we're going to do it. But that will come into play later in the course, in actually section 7.1. All right, so this is it for this section. This is a good place to quit. I'll see you in the next video.